Hi guys. So today we are going to be doing the same thing we've done multiple times this year. And we're going to do it one more time after today as well. And that is we're going to transform a new parent function. The only difference this time, this actually is a parent function that you saw in Algebra 1, but we're going to spend a little bit more time on it, a little bit more detail of it. So we're looking at the exponential parent function. So as we talked about last class, or your last online session, we talked about how the base for exponential really can be a lot of different things. But if that base is greater than 1, then it's going to have the shape of the parent function we're about to draw. So the parent function really is just the base to the x power. Okay, the x is in the exponent. It could be 2 to the x, it could be 4 to the x. Probably the most common ones you'll see are 2 to the x, e to the x, and 10 to the x. But regardless of what the base is, let's pick some points to plug in. So if I plug in 0, anything to the 0 power is 1. If I plug in 1, anything to the first power is itself. If I plug in 2, we would take the base and square it. If I plug in -1, it would become the reciprocal. And if I plug in -2, it would be 1 over the base squared. So then if we graph this, okay, it's going to have this same shape as the graph we talked about last class. And it's going to have that horizontal asymptote. All right, so now let's start talking about the features. Okay, so the features of this graph. The domain is -infinity to infinity. The range, it's everything above the asymptote, but it does not touch that horizontal asymptote, so it's a parenthesis, 0 to infinity. This graph is increasing everywhere. It is not decreasing anywhere. It's positive everywhere. It's not negative anywhere. It does not have any symmetry. It does have an asymptote. And it's really important to understand now, these exponential functions will all have one horizontal asymptote. Once we get to log graphs, it's going to have a different asymptote, and that's going to be a really important feature to distinguish between these graphs. End behavior is also a little harder to write on these. So as x approaches -infinity, let's look and see what our graph is doing. So as my x's get smaller and smaller and smaller, those y's are getting smaller and smaller, but only to a point. They only approach the horizontal asymptote. Then as our x's get bigger and bigger and bigger, our y's get bigger and bigger and bigger and are approaching positive infinity. All right, so what we're going to do now is look at the same chart you have looked at enough times this year that you're probably sick of it at this point. But all of our transformations, okay? Shift right, what that's going to look like on your exponential function. Anything that's happening in the exponent is going to be horizontal. Anything that happens out in front of the base is vertical, or outside of the base, I should say. Basically, if it's not in the exponent, it's if it's away from that base. So a shift right would be the base, and I'm going to use a capital B for the base just because lowercase b we've used all year for horizontal stretch and compression, and I want to keep that consistent. So x minus h in the exponent is a shift right. X plus h in the exponent is a shift left. Horizontal compression again in the exponent like that. And then if you have a negative in the exponent, we talked about this briefly last class when we talked about how exponential functions can show decay when they're reflected over the y. But again, that negative in the exponent is a reflection over the y-axis. All right, shifting up would be, again, outside away from the exponents. Shifting down away from the exponent. A number multiplied by the base is a vertical stretch. Okay, again, it's not part of the base. We can't actually multiply them together. That's your vertical stretch or compression, depending on the value. Then if you have a negative on the outside, that is a reflection over the x-axis. Keep in mind that negative is not in the parentheses. We do not have a negative base. That's not going to be an exponential function if we do. All right, what's also a little bit different about this graph, we're going to use the same method we've used all year, where we're going to start by shifting kind of our 0, 0 point. What's different and kind of unique about this function, though, if you remember, 0, 0 wasn't actually a point on this graph. 0, 1 was a point on this graph. The problem is we can't just shift 0, 1 because 1 is affected by stretches and compressions. All year we've been shifting that 0, 0 point because 0 times anything is still 0. But now that we have that 1 involved, we can't just shift the 0, 1 point. So what we're going to shift instead is what I'm calling the center of the asymptote, or basically your new origin. So whenever we do our shifts, we're going to shift this origin point, and everything will be in relation to that new origin point. So the way that I'll graph it is I'll just put a little star wherever that point's moved to. So it's not actually a point on our graph, but we'll still use it in relation to those parent function points that we're plotting. All right, so let's look at a couple examples. So the first thing we want to do is we want to identify the base, because the base determines what pattern we're going to follow after we've shifted that new origin point. It's also important to remember that the base is not a transformation. You may look at this and just think, hey, that's a vertical stretch by 7 because you're so used to seeing that. But 7 is not a transformation. That's just the base. The only transformation this graph has is left 1. Domain is going to be really easy for exponential functions. Every exponential function has a domain of negative infinity to infinity. Range is going to be determined by reflections and by your vertical shifts. So this graph has not shifted up or down at all. So it's just shifted left or right. So that doesn't change the range from the parent function. All right, looking at our next one. The base is e, because e is what has the exponent on it. That means the 3 actually is a vertical stretch. And this graph also has shifted down 5. Shifting down 5 is going to affect our range. Domain is the same. But again, since we took that parent function and we moved it down 5, that range is now going to be from the asymptote, which has shifted down 5, to infinity. Then the last one, that's a base of 3/4. Transformations, that 4 in the exponent is a horizontal, either stretch or compression. Because it's greater than 1, that is a horizontal compression. And this graph also has shifted up 1. Domain is from negative infinity to infinity. And then range is from 1 to infinity because it's shifted up 1. Now keep in mind with this, just like we talked about last class, that base is showing decay because of that 3/4, which means the shape of this graph is not going to be going this way, it's going to be going this way. But as you plug in those points, okay, the 0, 1, the 1 base, the negative 1, 1 over the base, you'll see that in case you forget, and that'll give you a pretty good clue as to what's happening. All right, so now we're going to go ahead and actually graph this. So what we're going to do first is we're going to identify the base. That way we make sure we know the base is not a transformation. On this first one, the base is 2. Then let's list our transformations. Negative out in front, that's a reflection over the x-axis. Then we've gone left 3 and down 1. Well, left 3 and down 1, again, that's typically where we put our vertex, or point of inflection, on a lot of those key points. Well, that's where we're going to move our origin. So left 3 and down 1, I'm going to put, that's 4, sorry. Left 3 and down 1, I'm going to put a little star. That's my new origin. So when I write my pattern, everything's still going to be in relation to that point. That point just isn't on my graph. What that point tells us, though, is where our horizontal asymptote is. So I am going to go ahead and draw that. All right, then let's list our parent function pattern. Over 0, up 1. Right 1, up the base. In this case, the base is 2. Left 1, 1 over the base. And I'm also going to do 2 a base squared, which would just be 4, to give me another point to make this a little bit of a more accurate graph. A lot of times when you use these reciprocal points, they're going to be fractions. They're going to be really hard to see on your graph. All right, now let's apply the transformations. So this has been reflected over the x. That means that I'm going to make all those y's negative. So from that star, over 0, down 1. Right 1, down 2. Left 1, down 1/2. And right 2, down 4. And that's my exponential function. All right, domain, range, and I'm also going to include end behavior. So domain here, negative infinity to infinity. Range, the lowest point on this graph is negative infinity. It keeps going until negative 1. And then end behavior. As x approaches negative infinity, as my x's get smaller and smaller, the y's are getting closer to the horizontal asymptote, which is negative 1. As my x's get bigger and bigger and bigger, the y's are getting smaller and smaller and smaller, and they're approaching negative infinity. All right, so let's try another one. Now on this one, you'll notice we've got that b value. Hopefully by now we're used to factoring that out. So I'm going to rewrite this as 1/2 x minus 6. Because again, if you divide by 1/2, you're multiplying by 2. That means the base is e. This graph has gone right 6, up 1, and has a horizontal stretch. So I'm going to go right 6, up 1. That is my new origin. That is where my horizontal asymptote is. All right, so everything's going to be in relation to that new point, that new origin. Parent function, anything to the 0 power is 1. Anything to the first is e. And then in this one, I know it's going to be a little hard to get these exact numbers. I'll go ahead and write this as 2.7 just so we can kind of estimate. If you want to square that, that's going to be about 7.3. And then this is going to be 1 over 2.7. And again, that's something that you kind of really want to use a calculator probably to estimate. It's going to be about 3.37. So this one, we're not going to have super accurate points, but we're going to get the right general idea. All right, then this graph, what we need to change from our parent function was that horizontal stretch. That means I'm going to multiply those x's by 2. So from that star, over 0, up 1, right 2, up almost 3, right 4, which is going to go off my graph, but I'm going to go ahead and show it, up 7.3, which will be up there, and then left 2, up 0.37. So there is my function. Oh, let me go back and do our domain and range. So domain is negative infinity to infinity. Range, the lowest y value is 1, keeps going to infinity. And then end behavior. As my x's get smaller, they're approaching that horizontal asymptote, which has a value of 1. As your x's get bigger, your y's are getting bigger. All right, then we got 2 more. Again, if you feel comfortable at this point, go ahead and pause the video, but we'll go ahead and do the same thing. We'll start by identifying the base. Our base is 4. Then let's list our transformations. We've got a reflection over the x from this negative. We've got a vertical compression. We've got a reflection over the y, and we've gone up 2, which means your new origin is up 2, which means your horizontal asymptote is y equals 2. So our points from our parent function are going to be in relation to that 0, 2 point. Parent function goes through 0, 1, 1 comma the base, negative 1, 1 over the base, and then I'm also going to do the base squared. Then let's see how we need to change those points. Reflected over the x, and vertical compression means I'm going to multiply that second column by negative 1/2. Reflection over the y means I'm also going to change the signs of those first numbers. So I'm going to go over 0, down 1/2, left 1, down 2, right 1, down 1/8. And you see what I'm talking about with those fractions. It can get really hard to tell. And then left 2, down 8. Domain is negative infinity to infinity. Range is negative infinity to that asymptote. And then as x approaches negative infinity, as my x's get smaller, the y's are getting smaller. As my x's get bigger, the y's are approaching 2. All right, last one. Base is 1/2, which again, that's going to look kind of like a reflection over the y. Instead of showing growth, it's going to show decay. But when we pick those parent function points, that'll make it clear as well. It's got a vertical stretch. It's gone right 2 and down 4. So right 2, down 4 is my new 0, 0. So everything's going to be in relation to that 2, -4 point. Parent function, we go over 0, up 1. Right one up the base. Left one, the reciprocal of the base. So that's going to be 2. And normally we do the base squared, but that's going to be a really small number to graph. So instead, I'm going to use -2 because that's going to be the reciprocal squared, which is 4. And that's just going to be an easier point to see. Now, you really only need 3 points to have a good graph. I like to include that fourth, though, just to make it a little bit more clear. All right, we've got that vertical stretch we need to consider. So we need to multiply and not use an eraser. Multiply by 3. So from that star, over 0, up 3. Right one up 1.5. Left one up 6. And left 2 up 12, which is almost off my graph. And that's my exponential function. Last features, domain, range, and then end behavior. So as my x's get smaller, y is approaching positive infinity. As the x's get bigger, the y's are approaching -4. All right, so your to-do for today is actually going to look a little bit different again. So already did the ed puzzle, hopefully. Answer the questions that went with that. The practice problems, it's only 4 questions, so really, really short. So in addition to those practice problems, there's a Desmos activity that's linked on Schoology. Now, on that activity, I need to give you guys a couple hints. First of all, you only have to do slides 8 through 12. All of the introduction slides are what we usually have, and that's just for you to kind of experiment and get some more information. You can move those sliders, see how it changes your graph, see what effects it has. So those are optional. Those just gives you guys a chance to see more about these functions. 8 through 12 is what's actually going to get looked at for grades. On those, when you get to those slides, the first 2 are just multiple choice. The last 3, it's the kind of questions we usually have where you're going to see kind of that dotted line graph. And you're also going to see the asymptote. And you have to write the equation that fills in that dotted line. Now, I'll tell you guys a couple hints. First of all, you need to read the words that are written on the left side, because that's going to tell you what the base is. If you don't know the base, it's going to be really hard to write these. I'm also going to tell you none of the graphs are going to have vertical or horizontal stretches or compressions. There will be no stretches or compressions, either vertical or horizontal, on any of these graphs. The last thing, once you find the correct equation, it'll fill in that dotted line with that solid line. The asymptote will not get filled in. Okay, the asymptote is just there to help you guys figure out what the equation is. So again, slides 8 through 12, look for the base in the directions. And then there's only going to be reflections and shifts whenever you write those equations. All right, if you need help, you got a couple options. You can email me, you can fill out that video request, or you can join that Zoom session that's going to be from 2 to 3. Once you're done with all that, you can do that week 3 assessment, which is going to include the stuff from Tuesday as well. All right, so let me know if you guys have any questions.